All right, well, good morning, everybody, and welcome to this February CRIN Project Cafe. We are going to cover some exciting topics today. We have a number of guest speakers lined up, so we'll run through a few basics here, and then we'll get to dive right into it. So today's topic fits into the carbon capture and value-add products theme area within the Clean Resource Innovation Network. And that covers a wide range of areas, starting from carbon capture, going into hydrogen, geothermal, and the value-add products would include critical minerals, as well as things like carbon value-add materials like nanomaterials, graphites, graphenes, etc. So covers all the fun stuff. So very excited to be presenting some good talks today. And I'm Dave Van den Assem. I'm the theme lead for the CCVAP or CCVAP area. I'm also Director of Clean Technology at Alberta Innovates and Director of the Hydrogen Center of Excellence for Alberta. We're going to start off with a land acknowledgement, so that should be coming up on the screen here momentarily, but as it's coming up, here we are. Realize that folks are calling in from a wide range of areas, so wherever you are, I invite you to take a moment now to reflect your relationship with the land around you and how it supports you, and take a moment to just honor that. Unless you're living on a boat, then take a moment to enjoy the water that's surrounding you and supporting you. Hopefully not surrounding you, but supporting you at least. And with that, maybe we will move on a couple of housekeeping items. First one is we're going to run the presentations one right after the other, and then we will have time at the end for questions. So be sure to take notes so you're keeping track of your questions, because if you have a question on the first one, but you don't write it down, you may not remember by the time the last of the riveting presenters will be doing their bit. So make sure you track your notes down. If you're online, the Q&A function will be where you want to document your questions, and we have highly capable, fabulous people that'll be managing that in the background. So when we get to that point, for members who are in the audience, then welcome, and you would just raise your hand if you do have a question at the end, and we have some roving mics. We will be able to get you set up that way. So just state your name, your affiliation, and then go ahead with your questions. That is the basics. So with that, we'll jump right in to our first presenter, Edson from G4 Insights, and Edson will be talking with us about PCH Reactor scale-up validation. And each of the presenters is going to be sharing their own slides. So presenters, a heads up, get ready for that. But take it away, Edson.
Thanks, Dave. Good morning, everyone. Okay, so G4 Insights, yes, we're a Burnaby-based company, and we've been working on this technology for about 15 years. Let's advance the screen. The technology is called pyrocatalytic hydrogenation, and the purpose of the technology is to develop a thermochemical process to convert lignocellulosic biomass, as forestry biomass and agricultural crop waste, into a large-scale, industrial-scale production of renewable gases, such as renewable natural gas or green hydrogen. And within 5 years, we expect to be able to produce the renewable natural gas at a cost under $10 per gigajoule. And also green hydrogen can be produced at less than $1 per kilogram. The advantage that we have is that our approach using a fast pyrolysis approach is about 50% lower capex compared to gasification. And as well, the technology can also be used for applications such as producing renewable syngas, power to gas, where renewable grid power, the excess grid power from wind and solar, can be used to combine with biomass and make renewable natural gas instead of just hydrogen. And also we can produce large amounts of high quality biochar with over 90% fixed carbon for carbon dioxide removal applications as well. So quickly go through how the technology works. The process is to hammer mill waste fibers like from forestry harvesting. That goes through a fast pyrolysis step, which creates pyrolysis gas. We add hydrogen, and then the combination of pyrolysis gas and hydrogen goes across commercially available catalysts. That converts those gases into methane and water. We drop the water out, we purify the methane, and that produces renewable natural gas. That's 98% plus methane and remaining hydrogen that can go to the grid as RNG. To make the added hydrogen, we are taking a portion of methane that we're making and putting that through a standard steam methane reformer. And that creates a syngas, which could be a product in itself, or purified to produce the hydrogen we need internally. In that purification step, there's an opportunity to capture the CO2, which is pressurized and purified for CO2 sequestration or downstream uses. In the pyrolysis step, most of it is going to gas, but we can actually have a biochar fraction that's left over that can be used as a fuel for the burner in the steam methane reformer, or we can configure the system to produce more biochar, and this can be used for the carbon dioxide removal or CDR credits, which are very valuable in the current market. If we want to make green hydrogen, you'll notice that the process blocks are identical because the technology is exactly the same. What we do instead is we take all of the methane that's produced and we put it through a larger steam methane reformer, and it gives us net green hydrogen output. The progress to date is that over the last 15 years, we've conducted some very high-profile demonstration projects. First major one was in California Energy Commission. We took forestry waste from the California area. We produced renewable natural gas, compressed it, and ran it in a unmodified CNG vehicle. 2019, we completed an end-to-end demonstration of continuous production of RNG and injected that gas into the Edson gas grid at both facility. The illustration in the middle is our current project, which is the reactor. So the reactor is one of 30 subsystems. This is the one that we want the intermediate data points for before scaling up to a full commercial plant. That's the current project that's being funded by CRIN and other partners. Some of the challenges that we've encountered is that we find ourselves in a very unique space. On one hand, there's very strong demand for commercial offtake agreements for RNG supply from your gas utilities. Very high interest for renewable project developers. Lots of money that's available for whether it's wind or solar. Renewable fuels is a hot topic, so there's a lot of money waiting to be deployed. And as well, we've had very strong natural gas industry support, whether it's the NGIF or other players. Great support from that community. The challenging part is that we're in that space where forestry companies, which is our feedstock side, are generally risk adverse, or if they have some in-house activity, it's going to be focused on their own in-house technologies as opposed to working with a third party or a non-university, as an example. Natural gas utilities are generally risk adverse. They're interested in offtake agreements. Generally don't invest in pre-commercial technologies. It's part of the mandate as a gas utility. And finally, the VC space this is difficult for them because it's a relatively high capex in the early phases and much longer time to exit. So it is not a good fit for VCs in general. So our focus has been to work with industry and government to get the partnerships and the supporting funding to move our projects forward through some of the projects that we've talked about so far. And we'll continue to use that route as our primary way of moving forward. Collaboration opportunities with perhaps some of the CRIN audience members. We're looking for strategic partners and investors to get us through to the commercial plant, which is our next build. So we're looking for project developers interested in doing G4 commercial scale RNG or hydrogen plants. CapEx is relatively small for thermochemical plants. We can be commercial in the 20 to 30 million CapEx, not 1 or 200 million, which is the other technologies required. And there's always an opportunity to look at the G4 equity investments as well. Next steps for us is to complete the current scale-up reactor, which is 3 ton per day nominal scale. And that gets us within reach of designing the full-scale commercial plant, which is 36 dry tons a day of biomass input. Output is about 450 gigajoules a day of renewable natural gas, or 2,700 kilograms of green hydrogen per day. And we're actively securing commercial sites and discussing with project developers and partners at this stage. That concludes my presentation this morning. I thank you.
All right, thank you very much. Looking forward to the question time for that one. Why don't we jump right into the next one? It'll be Soheil Khiavi of Hydron Energy. And Soheil's project is Waste to Fuel, accelerating commercialization of the lowest cost and smallest scale novel biogas to RNG upgrading system. So Soheil, whenever you are ready. How's that coming along, Soheil? Are you able to get the screen up? There we go. All right,
yeah, I have the screen. Thank you very much. Hello, everybody. I'm Soheil Khiavi. I'm going to walk you through a couple of slides. Not many, so I try to be very brief here, but if you have more questions, I can open up the others, backup slides. So our project is Waste to Fuel project, which we are taking biogas and converting to RNG. And today we are going to talk about the scale-up commercialization of our lowest cost novel upgrader. It's a smaller scale unit that is in operation. I'm going to touch base here about the global challenge that we have for the global emissions and the reduction of it. A lot of people working on electrification, and that's not probably the only answer. You need to have other technologies to deal with the hard to decarbonize sectors, such as heavy transportation and in heavy industries. And for that, specifically, some of the solutions are like biofuels or renewable natural gas and also hydrogen that could help to decarbonize this portion of the market that cannot be addressed with electrification process. So the solution that we have, Hydron, we're following or mimicking nature. We believe that nature is a brilliant designer and a builder with zero waste. There is no waste in nature. That's only waste we actually, human being, is making most of all the waste in our planet. And if you look at seashells, you look at silk fibers, these are the examples. Everybody knows that we are still trying to match some of the properties of these gifts from nature. And also, if you look at advanced solutions in nature that is provided for us, we are here talking, and we are actually an air separation unit and also a carbon capture unit running in our bodies. We take air and we separate oxygen using hemoglobin, and also we use anhydrase to remove the carbon dioxide and then exhale it. And these are the most efficient means of doing these separations. Compare that with the air separation unit, which is done at cryogenic temperatures, or a CO2 separation using pressure swing adsorption membranes. You're not walking around, we are not walking around with a backpack of boiler or a compressor hooked up to us to work. So what we do is marvelous separations easily. So what we're doing at Hydron, we're looking at this solution provided by nature, and we're reducing or cutting the capital and operating costs by making processes that similar to nature works under ambient conditions, pressures and temperature close to ambient, and with a better performance in terms of productivity and efficiency. All of that translates to lower cost. So the picture at the bottom there is actually a picture of our pilot plant that we manufacture and is getting tested. So we have a strong IP position. I won't go through that. We have developed a material, unique material, and we actually scaled it up over the last 3 years. And so we have a manufacturing facility now for the material, for our also rotary valves that they're dealing with conditions that requires in our pressure and temperatures that we are operating. So the manufacturing partnership that we have also with some of our partners helps us to build the balance of the plant. I'm just showing here several pictures of our valve design here, and also the inner core of our what we call them I-core or interrupter core. The technology is called interrupter, so we are not PSA or TSA or membrane. So it's a brand new technology. So it's an intensified regenerative operating technology. What we do in every cycle, our cycle is about 1 minute. In every cycle, we go through the full regeneration of the material, the same way that our body works. So your hemoglobin goes through full regeneration, grabs the iron 2, goes from iron 2 to iron 3, grabs the oxygen, and then releases. Same thing with anhydrous group. So it goes through full regeneration, means that you don't have buildup of contaminants, but also the material is fully selective for that particular species that we are designing for. For instance, if we design it to capture carbon dioxide, it will have 0 affinity to methane. Hence, our recovery is near 100%. And these are the things that we proved in the lab and in the field also. The scale-up manufacturing, as I mentioned, over the last year and a half, we focus on scaling up our material. We purchase large reactors, mills, coating equipment to generate material in the form of sheets. So we are using the same form of the structure that we developed back in Quest, their technology in the early 2000 for manufacturing our material to give us the superior advantage over the kinetics also, which is very similar to what in nature our body does. If you look at the lungs, there are these very small sacs that does similar high surface area ratio. So these equipments are installed and operational, and we started manufacturing our first set of the beds just about 2 months ago. So the pilot is, as I show you, this is the design, and also this is as built. I put a picture down here. It's my apology for bad quality. It was taken by a drone, so but I grabbed it out of a frame of a movie clip. But you can see the plant is there. The plant is built as a pilot test station, so we can easily remove different beds and different valve cores and try to use the technology for other applications. A platform technology, so we can do Biogas-to-RNG. We can also do syngas or any pyrolysis of syngas, and also various reformer syngas to generate hydrogen. So the plant in the picture above you see is two compartments, and this compartment that the small dummy standing is the classified Class 1 Div 2, dealing with the hydrogen or with methane. And on the right side, it is the office. So that's you're actually looking at with the same orientation. The back end is the operator's room, and then the rest is. So this first plant we built it mobile, smaller scale that could actually meet the techno-economic assessments that we require. So it can handle up to 200 cubic meter per hour of the biogas. It is designed currently to deal with only 50 cubic meter per hour biogas, due to the fact that we want to do a slipstream testing in several fields. The actual unit is on the wheels. I want to just go back to original picture and to show you here that this is sitting on a gooseneck and actually can be towed with a ton truck. So quite lightweight also. Of course, you need to empty the chillers, but the advantage of this technology is that it can be made mobile. It's very light. You can see the eye cores, the passage contactors. They are very lightweight. We are not using pressure to operate this. Everything is made of composite material, and this is a carbon fiber casing around it, and there is a fiberglass goes around it. It doesn't require high pressure, only fan and blowers. So once the separation is done, then we compress the natural gas, and that way, or hydrogen. That way, you reduce the compression energy by half. So this is the unit, and this is the gooseneck. So the unit complete, and it was transferred here on the gooseneck. This is off the factory. So this project, it's about 2.5 years that we've been working on this, and we started with IRAP and BC Innovate. Then CIC is taking the lead in funding us on this project. Now we have later on NGIF and also CRIN join the scale-up program, which we're going 10 times larger than this. Our business, I mean, this is not a business plan, really our commercialization roadmap. I want to just show you we started in December 2021, and we did our fat testing back in December, and the demo starts basically February this month. And
I'm going to give you about a minute to wrap here.
Yeah.
I want to keep on time. Thanks.
No problem. So we do our third-party TEA, and we have already 2 purchase orders for this unit. We received the purchase orders, and we're going to do the first unit manufactured in by March. So, and then the next one by August. 5 units is booked for 5 units to be basically booked for to be sold this year. The next stage we are going, I'm basically raising more money for the company to for the next round to do a 100 times volume production increase in our facility, so we can move to the new facility and increase our volume production by 100 times, so we can increase our sales from 246 million up to 120 million. There's enough room to go there. And this concludes my presentation. I want to thank the CIC and all other partners that help us in this project. Thank you for listening. If you have any questions, we're happy to listen.
Right. Thank you very much, Soheil. And we'll move right along to Kathleen O'Neill from New Wave Hydrogen. And she's going to talk about her project entitled A New Wave in Hydrogen Production. Kathleen.
Thank you, Dave. Hi, everyone. Let me load my slides. second. Get it to where? Okay, well, I'll just do it. I was going to turn the notes on, but I'll just wing it. I think we're fine. So welcome, everyone. We're here to talk about a new wave in hydrogen today. For the problem statement, I think many of you know that SMR, ATR, and electrolysis are the current most predominant methods of hydrogen production used globally. But they each have some drawbacks. SMR and ATR produce CO2 and use a lot of water. Electrolysis uses water and has a very high electricity demand and is somewhat expensive currently. And they both require parallel infrastructure built out, which is sometimes not particularly recognized. So for SMR or ATR to be green, it requires CO2 capture and CCS, and that requires a parallel build out of CO2 pipelines and more CCS facilities. And there are a few of them around the world, but where there isn't, it sort of limits the expansion of the clean production of hydrogen via these methods. And similarly with electrolysis, the electricity demand is really very high and must be renewable in order for electrolysis to be green. And the renewable power base around the world is not sufficient to support a rollout of electrolysis at this time. So it will require a massive build out of renewable power and transmission lines. And together, these parallel infrastructure dependencies actually will take decades at best and a very high investment cost. So we believe that the problem statement or what the market need is for a hydrogen production technology that can be rolled out and expanded in the very near term, and that is low impact, low cost, no water, and no CO2 production. So what we offer is a new wave. We believe that we check those boxes. Our technology is a method of methane pyrolysis, and similar to most other methane pyrolysis technologies, we don't produce CO2. We use basically temperature amplification to crack the methane molecule, CH4 into H2, hydrogen, and carbon, in our case, solid carbon. But what's different about our technology is the heating method. So instead of electricity-driven heating, like a plasma or other source that requires a fair amount of electricity, we actually use shockwave dynamics to increase the heat of the gases. So the feedstock gases, there's a driver and a driven gas. The driven gas is the feedstock gas. And the two of them are placed in this device called a wave rotor, which is essentially a rotating bank of shock tubes, if you will. And the shockwave dynamics, supersonic shockwaves that are set up in each channel around this drum are sufficient to transfer energy from one gas to the other through the shockwave dynamics and heat the gas. So we amplify the temperature of the feedstock gas to a temperature sufficient to crack that methane molecule. So it's a low electricity system. See, we are very fortunate to have a tremendous global partnerships and co-funders. So CRIN and our CAN, Alberta Innovates, ERA, and GIF, GRT Gas in Europe, and many outstanding universities and engineering groups that we've been working with. So we've been also fortunate in that from the very beginning of our company just a few years ago, we've had multiple grants in each year. So 3 grants from 2019 to 2021, 3 more in 2022 to 23, and a new one already in 2024. So this new grant actually opens up an interesting collaboration opportunity. If there are any out there that are interested, any industry partners or investors that are interested, it's excellent timing with this new grant. We have, between our current projects and our new grant, we have at least $6 million in a match that we can offer. And the timing is perfect in terms of our scope. So this is the scope for our current projects. We're able to take an industry partner's site as a case study and work through the design optimization, preparing engineering designs, techno-economic analyses, all the way through a short-term field pilot. So for the industry partners that join now, we could potentially use your specific site or your specific sector as this case study and accelerate you to commercial pilot. And challenges. Have we encountered challenges? Absolutely. It's been an amazing few years. And what have we learned? Mostly perseverance. It's really what it takes. So it's been an interesting ride, but tremendous. We have a tremendous team. We wouldn't have made it without them. We're also looking at the integration of hydrogen in agriculture, as actually the last two presenters are as well. So we are working with a group right now to explore the conversion of biogas into hydrogen at their site. We're also looking at virtually every market associated with hydrogen in the long run, from using natural gas, reforming it to hydrogen, biogas, creating clean hydrogen to produce ammonia, and vice versa. We actually believe that we've run some studies, some experimental studies and modeling to determine that we can use our system to reconvert ammonia back into hydrogen as well. So we're looking at hydrogen fuel, hydrogen power, and also green carbon. So I want to thank you very much. I think the contact slide didn't come up, but in any case, I'm Kathleen O'Neill. The company is New Wave Hydrogen, and we look forward to any questions, and I'm happy to send our contact information on request.
Excellent. Thank you very much, Kathleen.
Thank you.
We have one more presenter for this morning, and that is Walter Merida from the University of British Columbia and the coincidentally named Merida Labs, maybe. His project is deployment of low-cost, low-emissions hydrogen plant from natural gas pyrolysis. Walter, go ahead.
Thank you. If you could allow me to share my screen, that would be great.
Right, that should be coming up in half a second here.
There we go. Can everyone see the slide?
Yep, there it goes. Yep, you are
Okay,
good.
great. Good morning, everyone. My name is Walter Merida, and I have the privilege of joining you from the ancestral and unceded territory of the Musqueam people. And my project today is about making hydrogen from natural gas via pyrolysis. And this is a technology that started at UBC as a lab prototype, and in a little bit over 5 years, we have gone from a lab scale prototype to a pilot plant that is being commissioned as we speak in Fort Saskatchewan, Alberta. And the idea is very simple. Imagine a thermos bottle that you fill with metal instead of water, and then you seal that thermos bottle to eliminate the presence of oxygen. And then from the bottom, you bubble natural gas. Now, because the metal is molten and heated to such high temperature, as the bubbles of methane float up to the surface, they crack into hydrogen and carbon. And because the carbon is lighter than the metal, it floats to the surface of the metal column. And therefore, you can remove the solid carbon as a solid product and the hydrogen at the top as a gaseous fuel. And this, of course, can reduce or eliminate the generation of carbon dioxide because you simply don't have any oxygen to make dioxide with. As I mentioned, we have characterized this idea and prototype in the lab, and we are now building, we have built a pilot plant in Alberta. And as you can imagine, if you have renewable natural gas, this technology can effectively become a carbon sink, because you will be, using biogenic carbon, methane to generate the hydrogen. It also doesn't require any water, and it can use some of the natural gas to provide the heat, and that will, of course, result in some CO2 emissions. But if you find alternative ways of heating the metal column, then you can have effectively a zero-emission hydrogen generation technology. In terms of the progress, the idea, we had been thinking about it for a while, but we didn't really start working on this until 2021. We got a couple of funding grants to develop the pilot plant. And it has been overall an investment of about $10 million to go from, including the research work, to go from lab prototype to the pilot plant in Alberta. And the challenges, it is one thing to build a lab prototype in the lab, and it is a very different thing to build a pilot plant to get all the permits and all the engineering, contracting, and so on done. But we have successfully managed to go through those obstacles. And this is a rendering of the design of the pilot plant that we have prepared. And this is the existing plant that is currently being commissioned in Fort Saskatchewan. And some of the challenges were, of course, the permitting and contracting and so on, but others were just simply the fact that we had to actually commission the plant in minus 40 degrees Celsius temperatures. And while that was a challenge, it also demonstrated that the technology is robust enough, even at this pilot scale, to be operational under those conditions. In terms of the next steps, we are looking for partners. We are commissioning the pilot plant, and we would like to look at building the next plant in the 1 to 10 ton per day range. And I think that's all I have, and I'll be happy to answer any questions that you might have. Thank you very much.
Okay, well, thank you very much for that. And that is, that's the last of our speakers. So we are now open for the Q&A. So again, if you are in person here at the Energy Transition Center, we have roving mics, and put your hand up and give us your name and your affiliation. And if you are online, we will have the questions read out, I believe. So we've got one from the crowd here, please.
Hi, everyone. Mariam Omidvar from ATAX Energy. I have actually general question, maybe from Soheil and Dr. Edson. As they use the bio-waste as a feedstock for their technology, I was wondering if they look into if they want to scale up with the demand that Canada needs the renewable energy, how the feedstock could be a limit for the producing those renewable natural gas and hydrogen from bio-waste.
Well, I can go first here. Our technology is focused on lignocellulosic biomass, which is forestry waste. So in Canada, of course, and say Nordic parts of Europe, forestry is a huge opportunity for industry, and other parts of the U.S., where it's the West Coast or Southeast area, where the forest activity, when we cut a tree down, about 1/4, 1/3 of it is actually waste. So the tops, the branches, the sawmill waste, those are all inputs. These are normally just gathered and burned as roadside debris. We also have all the waste from proper forest management, that is thinning of some of the forest to reduce some of the wildfire risks that we have now, so that fuel load needs to be managed, and there's no commercial use for that fiber, whereas our technology uses that as an input. In fact, we can actually pay for a crew to go and get it. It's all part of the business model. So it's a huge opportunity in Canada.
Yes, thanks, Edson. And I want to add to following up the question, the technology that we have developed, because it operates at low pressure and near ambient conditions, costs about 50% lower than the commercial units out there. And this particularly increases the chances of many smaller scale producers of the biogas and the biomass to join the renewable natural gas grid. A lot of projects get canceled, or they can't pass through their first stage of economic study because the cost of the operating units and plants that are operating using membranes or PSAs or other technology quite high. And with lower cost separation, we believe that can enable the smaller producers of the biomass also to join, which they are actually making a significant portion of the biomass that is getting wasted nowadays. So we can actually help a bit with the situation by having this low cost upgraders.
I wouldn't mind maybe doing a follow-up question to that, and likely for the same presenters. So that is, you've talked about availability of the feedstock, but the distance between where the material, the feedstock is, and a plant could be, is also the other piece of it. And how are you working towards optimizing that? Are your facilities mobile so that they could be placed closer to the source of the feedstock, or are they centralized and you have to truck or pipe or some other means of getting that feedstock in? How does that impact the costs?
Yeah.
Sorry, Soheil. I'll tap into that. It's an excellent question. Our technology is sized to, say, a commercial scale, be sized to the residue around a larger commercial sawmill or pulp mill operation in Canada. So the collection area is identical. You're making the residue in a 30 to 50 kilometer radius around the sawmill operation. They're already active there. It's essentially the same type of skill sets to bring the biomass in. We've costed in the cost to bring the biomass in. Every sawmill has a natural gas pipeline running nearby. That is your injection point to get the product to market. So make the gas in northern BC or northern Ontario and distribute it to Toronto. It's a perfect setup for these remote communities that need the jobs and create high value opportunities.
Yeah, a little closer to source, but then once it's produced, then it's easier to transport.
Okay. And I wanted to add, I want to add, in fact, I actually mentioned during the presentation that we are making a mobile, because of a lower cost, we can make mobile units. And when it comes to biogas and biomass, it's a little bit different from the woody biomass. We're talking about problem around the production. So a lot of production is happening in the small hog farms and the small wastewater treatment plants. And in those cases, in fact, the issue of low quantities and dispersed version of the biomass actually causes more problem. In our case, what we do is that we work with what we call them virtual pipeline companies to we are working with virtual pipeline companies to, in fact, install the compressor and the storage unit on the sites that they produce small quantities of biogas. And these are the projects that in the past was not possible. So we're making those possible. Thank you.
Great. Thank you very much for that. Should we go to online? Are there any questions?
Please enter. Yes, Babak, I think that you had some questions online and you had your hand up. If you want to take yourself off mute, you can speak directly, or you can, I can address the question in the chat. It's up to you.
Okay. Hi, everyone. Hi, Soheil. Great to see you. I'm wondering that for your technology, you're kind of using a novel. I'm not sure, but can you explain a little bit more about your adsorbents or your system? Because to me, it looks like you have some adsorbent on the membrane and probably modified one with some like chemicals, and then that's how it's absorb CO2 at a very low pressure. I might be wrong. But when you say that it's like a zero methane loss or 100% recovery, that was like interesting to me. That how's it working, and also how your system is tolerant to VOCs, siloxanes, terpenes, all those like gases that are in the biogas, and how you can handle those. I mean, is it something like very sensitive to those, and you need like a very strict like pre-treatment like before reaching to your system?
Very good questions. So as I mentioned, the technology is not the adsorption technology. It is the way that it works is more with the coordination chemistry. similar to the same way that, as I mentioned earlier in my presentation, that when you're breathing in air, the oxygen gets separated because you have oxygens that they are in coordination with the iron ions in hemoglobin. And also when you're breathing out the carbon dioxide, that carbon dioxide is a very weak chemical bond. It's called coordination bond between carbon dioxide and hydrates, which is a zinc connected to histidine groups. So that's the way nature deals with it. And for that reason, it's very selective. That's why you can say very high recovery, 100% recovery. There are some there are some gaps in the valves and other parts that will be difficult to reach to 100%. So we actually say 99.9 or 99.5 recovery. And yes, a new material that we develop in-house and commercialize it. And it is for the first time this is happening. So that's why we've chosen a new name for the technology. But it's very much a copy or mimic from nature. That's what our goal of our company is, to look at how nature provides solutions, because we believe that there's a harmony there. And if we want to sustain a long life on our planet, we need to work with nature, learn from nature, and mimic the nature process in order to minimize the destruction that we are causing to nature. So what was the second part of the question? Sorry.
Yeah, it was about the VOCs and because you're dealing only with CO2, but what about the others? I mean, can your system handle it? And also, sorry, one more last thing is that what the flow rate that you can handle, you said maximum 200 NCMH. So usually in digesters, we have easily like 500-600 NCMH. So can your system scale up to that level also?
That's actually, those are good questions. First one, on the VOCs and other contaminants, for example, for biogas, you have H2S. A lot of adsorbents, PSA adsorbents, they have a problem dealing with H2S. And in our case, H2S actually is not a problem with our adsorbent, because it just basically gets removed with the carbon dioxide. But the reason we capture it before, because you don't want to release H2S with carbon dioxide to the atmosphere. And with the VOC is the same. So no effect, it passes through. So it means that we have to actually capture it. Prior to that, we're using activated carbon and other means. Our technology can be made in combination with commercial adsorbents. A part of our material could be activated carbon in the forms of these, what you call it, membrane, but they're actually, we used to call them a structure adsorbent. I call them parallel passage contactors. So they're parallel laminar flow contactors. So we do have commercial units out there that, in fact, it deals with VOCs and the siloxane also. So these solutions are easily part of our plant design. Now, when it comes to your last part of your question, what was that? I forgot. Can you repeat the last part?
Yeah, it's about the flow rate, like the capacity. So
yeah,
how easily it can go to, for example, 1,000 more.
Of course. I mean, this is our, as I mentioned, this is our first pilot unit that intentionally we designed it small enough. Every new technology creates a lot of people don't believe it. It creates a lot of people that they don't believe in it, and a lot of issues with that. And the best way dealing with it, I learned, is to build a plant and then send it to the people. So that's what we put our first plant on the wheels. But also there's a business case for the mobile units. So this plant is moving from site to site to show the performance to the customers. And we made it small just to make sure that it is not going to disrupt the site that it goes to, a slipper stream. The project that we have currently with CRIN and NGIF is the scale up by 10 times. So we go up to about 1,000 cubic meter per hour in this current project. So that unit that I show you and the presentation I had was about the project that we already completed, the pilot. And at the current state, we are at the commercialization of a scale up version, which goes 10 times higher, up to 1,000 cubic meter. Thank you.
Great, thank you for that. I have a couple of questions for Kathleen and Walter, but if there's a question from the crowd heading that direction as well, then I'll let you take it over. Go ahead.
Yeah, this is Rob Pride with Econa Power. The question is actually for Edson. You talked about steam methane reforming with RNG and a particular cost associated with that. Can you just comment on the scale or capacity of hydrogen production that those would have been referenced to?
Yeah, so our sort of sawmill scale plant, the input is about 250,000 tons of biomass a year, which is about 750 tons, dry tons a day of biomass going in. The SMR unit for that system would be about 40,000 cubic meters per hour. So it's a good sized refinery class SMR unit to produce 75 tons a day of green hydrogen at that scale at less than $1 per kilogram.
Perfect, thank you.
Okay, I'm going to jump over to a question for Walter and Kathleen, and then it looks like we have another one from the crowd here. So my question is more on the waste streams and how to manage them. So both of your processes are going to produce a solid carbon black material. And how are you looking at managing those? Because the volumes are going to be quite significant relative to the amount of hydrogen that's produced, as well as potential in the case of the molten metal piece, some potential separation steps of the metal reactant or catalyst from the actual carbon. And in Kathleen's case, it's going to be relatively solid carbon products, but you may have incomplete combustion, so you may have other materials, gases and whatnots coming out of that. So open that up. Whoever wants to take that one first.
Khiavi, would you like to
You
go?
go.
Okay.
Sure, okay.
Yes. Thank you. So that's a great question, and in a way, it will depend on the market. When we first started developing this technology, we were focused on the hydrogen production and characterizing the purity of the hydrogen. But then we very quickly realized that there are markets for the carbon products as well. And one of the advantages of our technology is that because it is a steady state process, unlike some of the other pyrolysis technologies which rely on plasma or non-steady state processes, we have a lot of control over the process variables, meaning feed rates, bubble size, residence times, temperature gradients, and so on. And what we have, and this is part of the IP development that we are currently going through, is we have realized that we can actually produce different types of carbon. And obviously, different types of carbon have different markets. And at the moment, we are just, even without doing anything with the carbon, so even if we just landfilled the carbon, the solid carbon, we believe we can produce hydrogen at under $2 a kilogram at $4 per gigajoule natural gas prices. So, that puts us within the window of the DOE targets in the US. And frankly, we are just trying to get the pilot plant characterized and the purity and composition of the products characterized. And then we will optimize the process for the different markets. But again, even if you landfill the carbon, you will have a hydrogen production at those levels.
Thank you. Kathleen?
Similar, actually, very similar with our system. But when we first did our commercial designs with some partners a couple of years ago, one of our engineering contractors did a full design for the carbon separation, pelletizing, purifying, upgrading, packaging for that carbon. So all of that is included in our capital costs. So we have a plan and a design to manage the carbon to a point where we can pelletize it and market it for sale or storage. Similar to what Walter was saying, our system is able to be, the operating conditions can be varied at multiple points within the system. So we also hope to look at varying the operation to produce different types of carbon in the future. Currently, we're focused on just as they are as well, the hydrogen, but we are looking very closely at the carbon in parallel. And have plans to do some experimental runs with different operating conditions to see how that affects the carbon quality and type of carbon that's produced. As far as combustion, we do believe that we'll get complete combustion when you look at the system as a whole, which includes both the wave rotor or the rotating bank of shock waves that I referred to, and the rest of the system, which has an extended reaction chamber and separation and purification systems. So overall, we do expect full combustion and pure products.
Okay, thank you very much. Do we have any questions from online? No. They're all answered in the chat. Okay, there is one more from the audience.
Rob Pride with Econa Power. This question's for Kathleen. You talked about the technology really being driven based on pressure. Can you just talk a little bit about if that's specific to natural gas transmission pressures typically, or do you have to boost in addition to that? And just give us a bit of perspective on compression requirements before feeding into the technology.
Sure. In our traditional design, we do leverage the pressure inherent in a pipeline. So that could be anywhere from 40 to 100 bar pressure when we use natural gas as the feedstock. So we do take advantage of that pressure. For any gas that's not converted in the first run through, the unreacted fraction, we do recompress and put back in. We recompress and reheat before we put it back into the system in order to get a continual high yield. In other designs, if we are using biogas or other systems or other feed gas that isn't natural gas or pressurized in a pipeline, some of them already are inherently pressurized based on the receiving system that we're getting it from, and others, if they're not, we would pressurize. Colin, one of our colleagues is on the line. Colin, if you want to add anything, please go right ahead.
No, I think you covered it very well. Thank you.
Right, thank you very much. Now, lightning round. One question from online.
Yeah, one question for Walter. What is the specific energy requirement you are expecting for your technology?
Well, in the lab, we have seen, so to give you a sense, electrolysis is at least 50 or so kilowatt hours per kilogram. We have seen our technology be 5 times more energy efficient than water electrolysis, and at least half better than some of the numbers we have seen published by competing technologies. Of course, that depends on the temperature. So there's a trade-off between temperature of operation and conversion rates, for example, or conversion percentages. And we are just trying to fine-tune the sweet spot, if you like, to balance conversion rates and energy efficiency. But at between 800 and 1,000 degrees Celsius, which is what we have been running the plant and the prototypes at, we look at significantly lower energy efficiency than water electrolysis. So significantly higher energy efficiencies compared to water electrolysis. About 5 times better.
All right. Well, thank you for that. And I think that takes us to the top of the hour. So with that, I'd like to thank everybody for the presentations. And thank you, everybody, for participating, either online or in person. And look forward to upcoming CRIN Project Cafes in the near future. In the meantime, if you liked what you saw, you're not a CRIN member yet, please feel free to jump onto the CRIN website and sign up. It's free. And then you get informed of all these events that are coming up in the near future. So with that, we will wrap it up. So thank you very much, folks. And until next time, take care.
Great talking to you. Bye-bye.
Bye.